If you're new to this series, I am trying to 3D print an RC helicopter from the ground up. And to start with, I dived into the aerodynamic design of the rotor blades. So check out my last two videos, and I've actually had a lot of trouble matching the recorded data back to the design code. Now this was really evident in my testing with the stock NACA 0008 blades, where the thrust values were good, but the torque and thus the power, which was derived from the torque values, were off by some margin. Revisiting my Leishman helicopter aerodynamics book, actually to start the rotor head design for this project, I came across this small section on micro air vehicles, which I must admit I do remember reading about 6 or 12 months ago, but completely forgot about. And a micro air vehicle is essentially a vehicle having a rotor diameter of less than 150 millimeters, but it can also still be a vehicle with a rotor diameter of, say, 400 millimeters. It's still considered a micro air vehicle. So some examples, where there's a ducted fan, hovering type of vehicle, we have a normal UAV, or essentially your RC helicopter. Even the big ones that what I have here are considered micro air vehicles. Now, this micro air vehicle chapter actually covers a lot about the operating point and the fact that they operate at low Reynolds numbers. But what is a Reynolds number? So, a Reynolds number is a dimensionless quantity that helps predict fluid flow, whether it be gas or liquid, by measuring the ratio between inertial and viscous forces. Now, for airfoils, it's written as rho VC divide mu. So rho is the density, which is temperature and pressure and humidity dependent. V is the velocity of the blades in our case, which is the tangential velocity, which I measure at the 75% radius, which is radius times omega, which is rotation rate in radians per second. C, of course, is the chord length of the blade, which is self-explanatory. And mu is the dynamic viscosity of the fluid. In our case, it's air, and it is the resistance to flow or shear. So micro air vehicles actually tend to operate at Reynolds numbers up to 2 to 3 orders of magnitude lower than a full-size helicopter. So how does that compare? So I looked at a Robinson R44, great helicopter, looks cool, and I compared that against the XK110 micro RC helicopter I have. So by using values that I could find on the internet, we see that the Robinson R44 Reynolds number is about 2.7 million, while the XK110 is 57,000. Now, if we do the math, the XK110 ends up being 2 orders of magnitude lower than the Robinson R44. So this essentially means that the XK110, our micro helicopter, is operating in a regime where thick boundary layers form on the blades, inducing large values of profile drag. So we need a way in order to account for this and to calculate it and include it in our code so we can make an accurate design. But what generally is a low Reynolds number? When would we experience this thick boundary layer and increased profile drag? So basically, a low Reynolds number, or where this would happen, would be below 500,000. And anything below this number, it would really affect our figure of merit or efficiency of the helicopter. Full-size helicopters would be 0.7 to 0.8, so that's 70 to 80% efficient, while our micro air vehicles, as you can see in the graph, are much lower. We're 20 to 40%. If we actually look at the XK110, we're only about 20% efficient, so we have a pretty low figure of merit. Another aspect of operating at a low Reynolds number is the airfoil characteristics also tend to be non-linear with respect to the angle attack. So as you can see here, the NACA 0012 at a Reynolds number of 54,000. We have two different slopes before we stall at about 8.5 degrees. If I was to take a linear line through the 0 point, it wouldn't match up that well, as I need to use the data off the slope in my calculations. So what I do is I will pick a pitch point. I will then pick a couple of points either side, and then I take the slope off that line. This is a bit more tedious, but it's also just something that you also need to be aware of when trying to do calculations at these low Reynolds numbers. By looking at the rotor wake and comparing a micro air vehicle to a full-size helicopter, we can see that the most notable difference is the thick, turbulent vortex sheets in the rotor wake. Now, these sheets are formed by the merging of the thick boundary layers from the upper and lower surfaces of the blade, where the blade operates with a Reynolds number below 10 to the power of 4. Now, the result is a wide, conical, turbulent inner wake region that occupies a substantial amount of the slipstream area. And the net result of this is you have large induced losses to generate for a given thrust, and at a higher effective disloading and a reduced hover efficiency. To account for this larger than expected induced losses, the induced power coefficient equation can be altered for a micro air vehicle as shown here by including a wake contraction parameter, AW. A value of 1 would be for an ideal ducted fan with no wake contraction, and a value of 0.5 would be for an ideal rotor with a 2 to 1 wake contraction. If it was 0.5, 4 times 0.5 is 2, and this gets us back to the original equation. So how does my data compare now? Well, it was not the saving grace I'd hoped for. I plotted all of test 3 and test 5, which use the NACA 0008 airfoil, which is the stock blades, as shown, and compared this against the plot shown earlier from Leishman's textbook. So in Leishman's plot, he compared a subscale rotor with a micro air vehicle rotor, which had a diameter of 150 millimeters, and fitted curves using momentum theory, which I've replicated here. In my altered code, I imported these test points and ran an analysis to find the best fit for the wake contraction factor and the induced power coefficient. This came out at about 0.35 and 1.3 respectively, and is fitted here with my data. An okay fit, not great. I then fitted the ideal figure of merit equation, so no wake contraction factor, or we've set this to 0.5, and this fitted the data points much better than taking this into account. So why the difference? My code considers a lot of losses already with the root and tip losses, while also including the inflow ratio at each step point. This with the interaction with X4 to get the correct lift slope and drag coefficient values makes it much better than momentum theory. Maybe my rotor is too large to be treated as a micro air vehicle and these effects are less prevalent. As I said in my previous videos, my test setup and way of measuring the RPM and pitch is less than ideal, and this would play a huge role in the results. So after a more refined test setup, I think it would be good to revisit this analysis and see how we compare again. So what next? Although a slight divergence this video, it has given me the opportunity to tidy up my blade element momentum theory code, making it more robust and fixing some power equations which I'd actually got wrong earlier. I'd actually forgot to include the induced power factor in some of the equations. So it was good to tidy this up. So this hasn't been a fruitless exercise. But from here, I'm going to just continue on, leave it as it is. We'll start our twisted blade design and we'll get into it. But if you have any experience with micro air vehicles, what do you think of this analysis? Am I on the right track? Help me out here.